Greetings and salutations, everyone. This is Carl Seward, professor of mathematics and statistics here at the Arizona College of Nursing, the Falls Church campus. And this video is Module 3. I title it The Normal Probability Distributions. And I hate the fact that we're not talking about this live and in person. It's actually one of my favorite topics to teach or to introduce in all of statistics. But here we are. You have an opportunity to watch the video. So here it is today. In this video, we'll be diving into what, again, I said the coolest topic in statistics, in my opinion, or at least in or the course that we'll be covering elementary statistics, and that is that of the normal distribution. So by the time that we are finished, you're going to see why the bell-shaped curve pops up everywhere in real life, from test scores to pizza cheese. Yes, even pizza cheese. So let's dive in. So here's the game plan for the video. First, you'll get familiar with the shape and the key features of a normal curve, and then we'll learn how to estimate probabilities using what's called the empirical rule. And then by the end of this video, you will be able to look at a bell curve and say, aha, I know exactly what's going on here. Thinking about this bell curve, I don't want to leave you in suspended animation. Before we dive deeper, I want us to actually take a look at this curve. You've probably seen this shape before. It is your classic bell-shaped curve. It's smooth, symmetrical, nothing too wild, just a really elegant way to show how data tends to behave. You will notice that mu, which is population mean, is in the middle. So when our data is normalized, and we can normalize data, that's outside the scope of this course, but for data that doesn't even behave in a bell curve manner, we can normalize it to be a bell curve. Again, we won't talk about that for the purposes of our course, but a lot of times by nature, data falls in this bell curve, and we can make the mean the middle of that data. You will notice if I go one deviation to the right of the data, you'll see mu plus sigma. If I go two deviations to the right, you see mu plus 2 sigma. And then if I go three deviations to the right, you see mu plus 3 times sigma. So those are deviations to the right. Similarly, you will see mu minus sigma, one deviation to the left, mu minus 2 sigma, two deviations to the left, and mu minus 3 sigma, three deviations to the left. So we will have deviations to the right, we will have deviations to the left. Anytime I do not specify the direction, that is to say deviations to the right or deviations to the left, you are to assume that I have taken both left and right. So if I don't tell you a direction, assume I've gone in both directions. And then you will notice that one deviation to the left and one deviation to the right is called one standard deviation of the mean. And 68% of the data, the majority of a good chunk of the data, 68% of it is in one deviation. If I go two deviations to the right and two deviations to the left, we call that two standard deviations and 95% of the data. Almost everything or everyone that you're trying to capture is in two deviations. And then if I go three deviations to the left and three deviations to the right, 99.7% of the data is captured inside of three deviations. So one would say, oh, well, Carl, what about that 0.3% or 0.3%? That is outside of the standard deviation. So that would be an unusual occurrence. This, by the way, leads us to this idea of the empirical rule. So I call this the normal distribution. It is also called the empirical rule. So let's take a look at that. To be sure, this is one of those powerful shortcuts in all of statistics, that is that of the empirical rule. It tells us that for any normal distribution, 68% of the data lies within one standard deviation of the mean, 95% lands within two deviations of the mean, and almost everything, again, 99.7%, falls within three deviations of the mean. So the empirical rule is like your quick estimate superpower. Think of it in that manner. It's a quick check superpower, is how I like to describe it. Let's review the must knows that you need to know for the normal curve. Number one, it's a bell-shaped curve where the tallest peak of the curve is at the mean. It is perfectly symmetrical, so the left mirrors the right, and the right mirrors the left. Thirdly, it approaches the horizontal axis, but never actually touches it. Like it's tried to reach, but it never quite gets there. So if I go back to the picture of the bell curve, you'll notice on the extremes or on the tails, it is approaching the x-axis, but it will never touch. There's this idea of this concept in calculus called the limit, where I'm getting closer and closer and closer. In fact, I'm getting infinitely much closer, but I'm never touching. The bell curve is behaving in a similar fashion. And the last thing I think I want to say on this is the total area under the curve is always going to be one. So even though I'm not touching the x-axis, for all intents and purposes, the area under the curve is one or 100%. So just keep this in mind because these basics are going to be really helpful in understanding probability on the whole. So now what I want to do is take a look at standard units and areas under a normal distribution curve. And then thinking about this, I'm shifting gears just a little bit. In this part of the lecture, what I want us to do is to learn how to turn a regular number into something called a z-score. Basically, a z-score is a standardized way of saying how unusual a value is. We'll convert the raw data to a z-score, and we can convert the z-score actually to raw data, and we can find the areas under the curve. And there's lots of cool tools that you can use to support this. So let's get started talking about the z-score. So what exactly is a z-score, you might be asking me. All right, I'll tell you. A z-score tells us how many standard deviations a particular value is away from the mean. So remember we talked about one deviation, two deviations, three deviations, but what if something is falling in between 68% and 95%? What if something is like 72% of the population? How would I calculate that? I would do so using what is called a z-score, where the formula is z is equal to x minus mu divided by the standard deviation, lowercase sigma. And then I want us to talk about what does the standard score or the z-score tell us. Once you have the z-score, it tells you a z-score, um, if a z-score is near zero, rather, the value is close to an average. If the z-score is a positive number, the value is above the average. And I can actually have negative z-scores. In a negative z-score, it will be the case where it's below the average. So z-scores are like the universal language of how unusual is this? Is this not unusual near zero, unusual in the positive direction, unusual in the negative direction? So I guess now that we've kind of set the table of the theory, I want to provide you an example. Suppose the average amount of cheese on a large pizza should be 8 ounces with a standard deviation of only 0.5 ounces. An inspector finds a pizza with only 6.9 ounces. And then the question becomes, how far from the mean is that in standard deviations? And is the pizza place in trouble? Are they in trouble? Are they more than 6.9 uh, ounces? Or that deviation, rather, I'm saying, is that deviation unusual? Let's see. So since we want to know the number of standard deviations from the mean, I'm going to convert 6.9 to a z-score. So I'm taking that x value, and you will remember 6.9 was the amount of ounces is made of cheese that I'm using for my pizza. So I'm going to say the z-score is equal to x minus mu divided by sigma. So that will be 6.9 minus 8 over 0.5. So therefore, what this is telling me is my z-score is a negative 2.20, or that the amount of cheese on the selected pizza is only 2.2 deviations below, because it's negative, the mean. And the fact that the z-score is negative indicates uh, that the pizza amount of pizza cheese is 2.2 standard deviations below the mean. And guess what? The inspector is not going to close the franchise. Okay. Uh, because the negative 2.2 is within the standard deviation in which I'm looking for. Again, go back and take a look at the problem. The problem talks about this idea of the pizza parlor should be 8 ounces. The pizza should be, a large pizza should be 8 ounces with a standard deviation of 0.5. So the 9.6 is negative 2.2. And again, the negative 2.2 indicates that it's below the mean, but the parlor will not lose the franchise because of it. Given an X distribution with a mean mu and a standard deviation of sigma, the raw score can be calculated using the formula X is equal to Z multiplied by the standard deviation plus mu. So that's a way that you can find the standard score. You can just plug that in. And then let's look at this guided exercise. Let's talk about Ezra. Here's a scenario that you might relate to: getting to class on time. So Ezra usually takes 17 minutes on average with a standard deviation of 3 minutes to get to class. On one day, it takes him 21 minutes to get to class. How many deviations from normal is that? Or in other words, I'm asking, he coming to class, it taking 21 minutes to come to class, is that unusual? How many standard deviations is normal for that? And what time corresponds to that z-score of negative 2.5? And whatever that time would be, would Ezra ever expect a commute that fast? So that means I'm implying that it's going to be fast. So if I look at this, I'm turning that 21 minutes into a z-score. I know that the mean value is 17 and the standard deviation is 3. You'll notice that your z-value is positive 1.33, and we should expect a positive value since 21 minutes is more than 17, right? So that means my z-values are positive. That's above the mean. So as soon as I said Ezra was walking 21 minutes when the average is about 17, oh yeah, I better get a positive number. And similarly, if so, plugging that in, the z-score, and let's just say the z-score, oh, I put the wrong z-score in there. No commute time at or less 2.5 standard deviations below the mean, so that's 9.5 minutes. So no, that's right. The good news is I won't ask you a question to convert the raw score, the data score, the z-score to the raw score. I won't be asking you that, but this is a good formula to know. And then you'll see I'm going to continue to talk about this standard normal distribution curve. And then let's actually look at an example. So using the area to the left of z is equal to negative 1.0, what's that area? And then what is the area to the left of 1.18? In order to do this work, you're going to need to get familiar with the Z table. So let me see if there's an easy way for me to do that. Otherwise, I'm going to have to create a second video for when I switch over. So actually, maybe not. I'm just going to go dark for a second. And then I'm going to show you a Z table. Let's see if Microsoft Teams will be kind to me. Let's see here. Are you being kind, Microsoft? I mean, not Microsoft Teams, but what is this? Zoom. Let's see if Zoom is going to be kind to me. Let's see here. If not, I'll create another video. Zoom, are you being kind? Yes. Now, I've marked on this Z table, so I'm going to have to get to another Z table. But this is really actually a good example that we're marking up. So if I'm interested in the Z-score of 1.23, notice I'm using these columns. This column, the Z column, gives you the first digit and then the second digit. And then these other columns represent the third digit. So notice earlier when I was doing some work, I was looking for the Z-score for 1.23. I found 1.21 here, 1.20, 1.21, 1.22, 1.23. 1.23 is 8907. That's the area under the curve. Similarly, if I went to 1.18, I would go to 1.1, 0, 1, 2, 3, 4, 5, 6, 7, 8. That will be 0.08810. And similarly, I can do this with a negative because, right, are all things going to be positive? Heck no. So if I have a negative Z-score, I'm going to follow the same logic, except it's going to be with negative numbers. Let me see if I can pull this. Yes, I want to show you this. This is important. Stay with me. Stay with me. Stay this long. So watch this. With these negative Z-scores, if I had a negative 1, right, as a Z-score, I would just go to negative 1.00. And then the Z-score would be 0.1587 for that to the left. And then, let me not share here. So that's how you read the Z table. Z tables are pretty cool in my opinion. That's just me. And that's how you would read it actually. So I'm going to look at the next problem. But first, let me make sure that I get this right. Hold on for a second. Be patient with me, please. Trying to work the technology instead of the technology working me. See, that's how that works. Okay. Okay. So solution 2, we found that. And then let's look at example 3. In this example, we can use table 5 from the appendix to find the area under between 1.0 and 2.1. I'm going to actually want to go and actually work out the math in here. So I'm going to actually create this as another video. There's only like 3 more slides after this, so I'm going to create like a companion video so I can actually show you how I would do these problems. You're going to need a copy of the Z table, so I'll make sure that I send that to you, and I'll make another video to show you the examples of how to calculate the Z score.